What if everything you believe about the origin of life is wrong? What if life on Earth didn't start here, but came from somewhere else, carried through the cosmic void in frozen rock fragments, surviving a journey that should have been impossible? This is the theory of panspermia, and it suggests something unsettling. Maybe we're all aliens. Not in the science fiction sense, but in the literal sense, descendants of organisms that traveled billions of kilometers through deep space to seed this planet. Panspermia isn't just a radical idea. It's a scientific theory backed by growing evidence, and it completely changes our understanding of who we are and where we came from. To understand why panspermia makes sense, we need to go back 4.4 billion years. If you could travel to that time, you wouldn't choose Earth as life's cradle. The planet was a volcanic hell, constantly bombarded by asteroids, with a molten surface and toxic atmosphere. But Mars was different. Smaller and cooling faster, Mars formed a solid crust and developed liquid water long before Earth, a 100 million year head start. Evidence from Martian meteorites and rovers like Perseverance reveals a vibrant world, rivers winding through ancient valleys, lakes filling deep craters, and a vast ocean covering the northern hemisphere. Primitive Mars had everything life needed to begin. In Jezero Crater, where an ancient river delta deposited sediments billions of years ago, the Perseverance rover discovered something extraordinary, a clay rock called Chayava Falls. This rock contains pale leopard spot patterns, rich in minerals and organic molecules that on Earth often indicate microbial activity. So far, scientists haven't found a natural explanation for these patterns. That means these spots might be fossils, ancient Martian microbes, and our first real glimpse of extraterrestrial life. If this is confirmed, Mars isn't just a dead planet. It's the forgotten cradle of life, and perhaps ours too. But if there was life on Mars, what happened to it? About 4 billion years ago, a storm of asteroids struck the red planet. On the surface, these impacts were apocalyptic, destroying oceans, vaporizing the atmosphere, turning Mars into a frozen desert. But underground, something different happened. The residual heat from major impacts created thousands of mineral-rich underground water systems that remained warm for millions of years. These geothermal pockets were perfect incubators for life, protected from the chaos above. While Mars died on top, life may have thrived below, hidden in deep aquifers where cosmic radiation couldn't reach. But the bombardment had another unexpected effect. Each impact launched billions of tons of Martian rocks into space, scattering them throughout the solar system. Some of these rocks hit Earth. Scientists estimate that over billions of years, Earth received trillions of Martian fragments. In 1996, one of these rocks was found in the Allen Hills of Antarctica. Called ALH 4001, it formed on Mars 4 billion years ago, was ejected into space by an impact 17 million years ago, and fell to Earth 13,000 years ago. Inside it, scientists discovered microscopic structures resembling fossilized bacteria. Though the debate continues, this discovery raised a fundamental question. What if these rocks brought not just minerals, but life? For panspermia to work, life must survive a hellish three-stage journey. First, ejection into space at speeds exceeding 18,000 km/h inside rock fragments whose surface is superheated to over 1,000 degrees Celsius by atmospheric friction. Second, enduring the long crossing through the frozen vacuum of space, deprived of water, air, and nutrients for millions of years, while being bombarded by ultraviolet radiation capable of destroying DNA. Third, surviving re-entry into a new world when the frozen fragment transforms into a fireball while crossing the atmosphere at 40,000 km/h. No life form should survive this, but life is full of surprises. Spores of the bacterium, Bacillus subtilis, were found alive just a few millimeters below the surface of rocks, whose outer layer was superheated to over 400 degrees Celsius. While the surface burned, the interior remained cool enough to preserve life. Tardigrades, tiny eight-legged animals, were exposed to the vacuum of space for 10 days without protection and survived. They achieved this thanks to a protein called DSOP, which forms a protective cloud around DNA, blocking radiation. But the true resistance champion is the bacterium Deinococcus radiodurans. It withstands radiation levels 1,000 times greater than lethal doses for humans. Its superpower is the ability to reassemble its own fragmented DNA, reconstructing its entire genome in just a few hours. These discoveries prove that life can survive space. Even if organisms die during the journey, the final result might be the same. The remains of dead microbes contain DNA fragments that carry valuable genetic information. When these fragments fall onto a primitive planet with liquid water and organic compounds, they can integrate into the primordial soup, providing ready-made materials that accelerate the emergence of life. This is the theory of Panspermia, life seeded by cosmic corpses. Like manna falling from the sky, life's essential molecules may have rained down on young Earth, originating from an ancestral branch of life that began on another world. If this is true, terrestrial life was written with borrowed words for a story that started far from our shores. But maybe it was the other way around. Maybe Earth was life's cradle and Mars the receiver. Millions of Earth rock fragments reached Mars over billions of years. But due to its closer orbit to the Sun, Venus may have received up to 100 times more Earth fragments. Together, these three planets formed an intense meteorite network, sharing billions of fragments over billions of years. Some rocks traveled as far as Jupiter and its moons, potentially seeding the subsurface oceans of Europa and Enceladus. Even Saturn would have received millions of Earth fragments, some falling into Titan's liquid methane lakes. Seen from this perspective, the solar system isn't a collection of isolated worlds. It's a constellation of life, mixing its biochemistry along an interplanetary highway of asteroids. But this might be just the tip of the iceberg. In reality, life may be connected not just between planets, but between entire stellar systems. The average distance between neighboring stars in our cosmic neighborhood is about 4 light years, nearly 40 trillion kilometers. Making a journey like this would take millions of years, making survival even less likely, but not impossible. Studies show that microbes protected within a meter of rock can survive deep space cosmic radiation for tens of millions of years. Comets could be the perfect interstellar arcs. Their thick ice layers form a natural shield against radiation, protecting potential microbial passengers during the long crossing between stars. The best way to reduce distance is to bring stars closer. Most stars in the universe are born in dense clusters, where hundreds of young suns group close to each other. In these densely populated cosmic regions, the distance between stars isn't measured in light years, but in light months or light weeks. Our own sun was born in one of these stellar nurseries, with neighbors much closer than they are today. During this period, which lasted up to 90 million years, our solar system and its nearest neighbors may have exchanged up to 30 quadrillion solid objects. Up to 200 billion rocks from young, fertile Earth may have reached extraterrestrial stellar systems. If we ever land on worlds around neighboring stars, we might discover they're part of our family tree. Some stellar systems may be even more interconnected. Globular clusters, dense swarms of stars orbiting our galaxy, contain millions of suns grouped in a compact sphere. For planets located in these clusters, the night sky would be permanently illuminated by thousands of nearby stars, some shining as bright as the full moon. In stellar densities like these, an asteroid carrying microbial life wouldn't need millions of years to reach another stellar system, but perhaps just a few thousand. Interstellar panspermia would be inevitable. Every habitable planet in these clusters could be seeded repeatedly, creating an interconnected network of life spanning millions of stars. But there's an even simpler way to survive a long interstellar journey. Take your home with you. Throughout our galaxy, billions of rogue planets wander alone in darkness, ejected from their original systems by gravitational interactions. Their surfaces freeze at temperatures near absolute zero. But deep inside, some may retain a molten core capable of providing heat to a subsurface ocean, a perfect sanctuary for an interstellar voyage. Below the frozen crust, entire biospheres could float safely in the void for millions, even billions of years, using the planet itself as a spaceship. A few lucky ones might even complete the epic journey to a completely new galaxy, potentially making panspermia an intergalactic phenomenon. But what if life didn't need to travel on a planet or rock? What if it could float freely through space? By creating a living shell that retains heat and blocks radiation, communities of cells could weave their own itinerant habitats, self-sufficient bubbles of life floating in space like tiny living planets. Inside, they'd have liquid water, recycle nutrients, and use distant starlight as an energy source, never landing on a planet. By optimizing their size to just a few meters wide, strong enough to withstand pressure yet light enough, they could wander through space like cosmic plankton, spreading throughout the galaxy. Perhaps even stranger creatures wander through space. Imagine a creature so vast it would rival the size of planets. It would glide gracefully through the void, guided by an internal organ capable of sensing the faint gravitational pull of distant suns. Despite its completely alien nature, this titanic creature would cross the darkness for a familiar reason: raising offspring. It would use entire worlds as incubators, depositing eggs in primitive oceans where its young could develop protected. When mature, these young creatures would leave the planet and return to space, continuing the cycle. It sounds like science fiction, but in an infinite universe, life forms that defy our imagination might be inevitable. But the most likely way for life to spread between planets won't be organic. Like cosmic gardeners, advanced civilizations could seed life throughout the universe, perhaps as backups of their own species. They could treat the galaxy like a giant flower bed, spreading seeds and watching how they take root on distant worlds. Autonomous probes equipped with genetic libraries could travel for millions of years, identifying habitable planets and releasing microorganisms designed to thrive in different environments. These civilizations wouldn't just be exploring the universe, they'd be cultivating it, ensuring life never disappears completely. And maybe we'll discover that our own tree of life is just a branch from an ancient, vast experiment conducted by another civilization. Maybe Earth was intentionally seeded billions of years ago, and we're only beginning to awaken to this reality. The idea that life can be nomadic touches us deeply because we were nomads too. Our irrepressible need to explore and colonize new worlds is perhaps our oldest instinct. And if our origins truly lie beyond Earth, then the stars are more than just destinations. They're the branches of our family tree. The theory of panspermia doesn't answer where life originally came from, it just moves the question elsewhere. But in doing so, it radically expands our understanding of what life is and where it can exist. If life can travel between planets, between stars, between galaxies, then the universe isn't a collection of isolated worlds. It's a living organism, constantly exchanging genetic material, spreading the seed of life everywhere. Every habitable planet is a node in this cosmic network, connected to all others by trillions of rock fragments wandering through the void. Today, missions like the Perseverance rover on Mars, the Europa Clipper probe heading to Jupiter's moon, and the James Webb Telescope observing distant exoplanets are searching for signs of life beyond Earth. If we find life on Mars, Europa, or Enceladus, the first question will be, did it arise independently or is it related to us? Analyses of extraterrestrial DNA could reveal whether we share a common ancestor, definitive proof of panspermia. And if we discover that life on other worlds uses the same genetic code we do, we'll know we're not alone. We never were. We're all part of a single tree of life that extends throughout the cosmos. Panspermia forces us to rethink our identity. We're not just Earthlings. We're children of the stars, descendants of microbes that survived impossible journeys through the cosmic void. Our DNA may carry memories of worlds we'll never see, of evaporated Martian oceans, of frozen comets wandering between stars. And if this is true, then our mission isn't just to explore the universe, it's to continue the cycle, seed new worlds, spread life, ensure the flame never goes out. Because if life came from outside, then it's also our destiny to carry it forward. If you enjoyed this video, subscribe to the channel and hit the bell icon so you don't miss the next episodes about the mysteries of the universe. Leave in the comments, do you believe life on Earth came from space? Which theory about life's origin makes the most sense to you? Share this video with anyone who's also fascinated by the secrets of the cosmos. In the next video, we'll explore the subsurface oceans of Europa and Enceladus, worlds where life might be thriving right now, hidden beneath kilometers of ice. Until then, Keep looking at the stars. They might be more familiar than you think.